All right, looks like we're up and running full screen. Yeah, so this is a little addendum to video that I did a couple of days back. Geometry to algebra to calculus, and I got to the end of the whiteboards in the room, and I had just a few more things, 4 or 5 more things to point out about early calculus considerations. And so I thought I'd just do a little quick 5-6 minute video here. Hopefully not much longer than that, but to tie together some of the things that came out of that first video. All right, so just to rehash a little bit, we looked at a cubic. We looked at why it wasn't changing at that instant. All right, and I cubed 0.001 and got that amount of change, and then I contrasted with cubing 2.001 got me 8.0120060, and we can see significant change in the first 3 decimal places and no change in the first 3 decimal places of this calculation. And that's why it's not changing much there. And everywhere else, the change was an increasing change. This is a 12-to-1 basic average rate of change at 2 to 2.001. But if we were to get more decimals, I'll do 5 decimal places here. It would have been no calculator needed because of the geometric situation here. 0.000121234 1 2 3 4 5. Okay, we can see that the first 3 decimal places, well, we're doing 5 decimal places here, right? Changing by 5 decimal places. We're still getting a 12-to-1 ratio. But this is more accurate. This is more accurate. If I were to divide the whole thing by 0.00001 and this whole thing by 0.001, that's a little more accurate representation of the change from 2 at 2 to one-sided limit. But again, this is really the notion of a limit. I don't want to say much more than that at this stage, but we had the manipulative change in volume, which was this layer of change. If this was a 2 by 2 by 2 box, that's in the other video, then this sleeve gets a little bit more volume when I attach it to the box. The box is a little bigger, just a little bigger. And it can be represented by the change in volume. Well, we could represent it over here as the change in volume was 0.012. It came from 3 times 2 squared times 0.001. Well, that's getting us this representation of volume. And the most interesting dimension, because we can see 3 squares, right? 1, 2, and 3. The most interesting dimension is really the thickness of what I add, right? So in a 2 by 2, let's just look at this one square situation. We have a 2 by 2, but I'm adding just a little bit of 0.001 to that length of 2. It's hard to draw, such a small amount. It's hard to draw, but you can envision it. I actually do another video that spells this whole process out, but for y equals x squared. It's easier to see, and that's entitled The Relationship Between Differentiation and Integration. It goes into this more detail. So feel free to look at that. But let's see where I'm at now. I diverted a little bit. And that also talks about a layering machine, which I'm going to get to in a moment, a little bit further down the wall here. But you know, it deals with y equals x squared, the change in y or the change in x equals 2x, so on and so forth. And so let's change this now to y's and x's. So dy can be referred to as a little change in, you know, a difference in the volumes is equal to 3x squared dx, because we work with x's and y's for the most part in mathematics. So let's bring this down a little. All right, so I don't think you saw what I was talking about a moment ago. I apologize for that. But talked about doing this whole process with the square. I think it's easier to see the numbers, so feel free to look at that. But where are we at now? we're at a little bit of a calculation here. And what would happen if we just move this multiplication, because that's really multiplication, to this side. Then we're getting ourselves a formula for how the cubic changes at any instant. For instance, at 1 squared times 3, I'm going up at 3 to 1. And x is 2 squared, I'm going up at 12 to 1. When x is 3, 27 to 1, so on and so forth. We get a little feel for, the emergence of a slope field. And we could do the same thing with the negative numbers. They're just a little harder to work with. All right, so that's kind of where we're at, and that's really what a derivative is in calculus. A derivative measures the rate of change of the functions you're going to be studying, which are, you're laying the groundwork for it now, understanding exponentials and logarithms and sinusoids and so on and so forth. You're not going to have a hard time talking about the rates of change if you don't master what these graphs look like and how we work with them. So that's got to happen before you get to this. So good luck with that. But let's dive in a little more deeply still, because I don't think I'm going to be carrying this around in my pocket. Right? I'm not going to be carrying this box around in my pocket. So what helps us understand this process? Well, 3x squared is a parabola. And what I'm suggesting is that 3x squared dx is a product. And a lot of students, when they first study integration, when you integrate 3x, we're going to in a minute, equals x cubed plus c, and we're not going to worry about the c too much at this stage. People say, well, where'd the dx go? Well, if that's a product, I mean, I can make a product. 3 times 4 is 12. I could ask you, where's the 4 go? Part of the process. It's part of the numerics. And that's the same thing, really, that's happening here. But what is 3x squared? It's a height on a curve. Well, if this is 3x squared, then that height is 12 units, right? 3 times 2 squared. And what's the dx represent? Well, it actually represents a little bit of width. Right? I mean, I think I could have done a rectangle in any capacity. I could have put a little bit of change in x times 3x squared. Gets me the area, 3x squared dx. Just depends upon what the x values are. What are the x values that we're working with? Well, every number on the number line. But what's the size of dx? Well, in one instance, we kind of mimicked it over there by 0.001. The next time we mimicked it by 0.00001, right? That's somewhat conceptual. So we can think of this as a small change. And the smaller the change, the more accuracy we get, like a Phillips head screwdriver. More accuracy, more accuracy, more accuracy. I can show that here a little bit. Let's pretend that this is just one rectangle from 2 to 2.001. Okay, well then I could be measuring that area, and that area would have some error. But what happens if I make it 2.001? Well, that means I'm getting closer here to 2, and I've got a square that looks like that, or a rectangle that looks like that, and the error has been minimized. All right, well, what's preventing us to doing more decimals? Forever. Well, I'm just getting a strip of area. But now let's go back to calling this 2, and let's actually call this 3. Now, this is not drawn to scale, right? This is not drawn to scale. Obviously, 0's over here. But couldn't I just do layer after layer after layer after layer after layer after layer? And of course, my height's not 12 anymore. It's going up to a height of 27 over here. 3 squared times 3 is 27 over here. 2 squared times 3 is 12. And I get myself, a rectangle. I got a rectangle from 2 to 3, 1 unit going to the right, and 1 times 27 is 27, but there's a lot of error in thinking that way, right? So we want to eliminate that error. We do it by adding an infinite number of rectangles under this curve. Each one has a little bit more volume to it than the previous one. And if we add up, that's what that symbol means, to add up. each of those strips, well, we got ourselves the cubic. All right, now let's just see if we can kind of see adding up from 0. Can you painting, each layer of paint a little bit bigger than that one. And in the other direction, I'm moving in the negative direction, so my widths are negative, heights are positive. Okay, and that's what you're trying to visualize, this process. So what does that mean? Well, that means that we can take any function. Once we prove, well, I guess I got to prove it numerically over here, that from 2 to 3 equals the cubic. Now we don't worry about C now because we have an actual area from 2 to 3. And if I cube that, I get 27. And if I cube that, I get 8. If I take that difference, I get 19 units of change. And I do believe 2 gets me 8 and 3 gets me 27. And how much has the volume accumulated from 8 to 27? 19 units. There it is. And that's really the first fundamental, or some people call it the second fundamental theorem of calculus, which is as follows: the integral from A to B under some function that we're talking about layers is going to get us a big function, f of b minus f of a. Right, and that's a theorem in calculus. And I'm not talking about as well as I'd like to right now, but it's early in the morning and I'm still waking up. But let's just take a generic function here. And let's see if you can picture what the parent function is. If I start adding strips and strips and strips and strips of area and add up each of those as I go along. Each of those as I go along. Can you picture that maybe we're accumulating area, but less and less quickly? I mean, this strip of area added to that appears to be a smaller strip than a previous one. So we get this kind of trajectory. And then, of course, my altitudes now are negative, widths are still positive, so I'm adding negative area. And this, if I drew it better, offsets that, so it comes back to 0. And then I continue adding negative area, but less and less quickly, so it goes to a minimum where this offsets that. And then I start to repeat what I did at the beginning. It brings me right back to there. Well, it turns out that if this was the cosine function, and maybe you recognized it as the cosine function, depending upon where you are in your high school career, that starts at 0, 1 and goes to 1, 0. And what happens in the first 90 degrees to the heights in the unit circle? The heights do what? The first 90 degrees, they go from 0 to 1. Okay, so this is pi over 2. Pi over 2 gets me 1. This is pi. Sine of pi is 0. What's the sine of 3 pi over 2? So at 3 pi over 2, I go to -1. And then back at 2 pi, I come back to 0, so on and so forth. So the area accumulation under the cosine curve, starting at 0 and going to 2 pi, this is 1 unit, 1 positive unit, this is -1, this is another -1, this is +1, and I end up back to where I started from. So that's going to get me the sine, oops, I forgot to put the dx. All right, this is the height of the rectangles, this is the width, and it's producing this function, and we're not going to worry too much about point C right now. But if I go from 0 to 2 pi, I can see the area adding up. And so I go from 0 to 2 pi, which is really 0 minus 0. And I haven't accumulated any area. I mean, I've done a lot of accumulation, but it offsets itself. So anyway, I hope I captured that. I don't think I centered that video too well. Again, forgive me, it's a little early in the morning. I haven't had my coffee. But I just wanted to at least get that discussion started. And so now that it's started, we can maybe do a little simple calc as we do our simple algebra. I know some folks in the room are understanding it, and others, well, if you keep looking at it, you got a shot at understanding it. But if you're not having these conversations on a regular basis, and well, I mean, repetitions is everything in math. Um, I mean, how did you learn your times tables? You probably sat there and did a lot of mechanical work, looking at it, saying it, looking at it, 5 times 7, 35. Well, at one point, you didn't know 5 times 7. Got to work at it. And that's how this language is different than parlez-vous français. You know, you got to work a little harder at grasping some of the concepts that come your way, but it's still a language. When I ask you to do this, integrate 2x dx, I want this to have meaning. I want you to understand where these things come from and why it creates x squared plus c. Okay, conceptually. Otherwise, you're just working mechanically. And you'll be like most folks who, like myself, when I took calculus, and I didn't know what I was looking at. No clue. I mean, I could memorize some formulas and whatnot, you know, kick back on a test. But I couldn't conceptualize any of this. It wasn't until I started teaching it and asking myself what's going on and digging deeper into it that I figured it out. Right. And I had a bunch of calculus classes that I took for, you know, trying to get at what's going on here. And very seldom, no, I can't say very seldom. I never had any pictures drawn of cubes and squares and things like that, but that's what makes sense. So putting it out there. All right. Hope that helps somebody.